I'm going to give a short introduction to the Zircon Raman thermochronology, like a topic I worked mostly on during my PhD studies. And to begin with, so this is obviously a new method or a new dating method for zircon dating in thermochronology. And first of all, we can ask the question, why should we bother developing new tools or new methods? I think it's pretty straightforward, but anyway, I will give a short justification. So as we can see here in that sketch on the right, I hope everybody can see it. For all of the different dating methods that we already know, they all have different temperature sensitivities as expressed by the closure temperatures given here. And so this depends on the dating system, on the decay system, on the mobility of the daughter isotopes or the products, and on the mineral that we date. And so every method is pretty individual because it needs a different mineral, it uses a different disintegration system, and it's measured differently. So we always have to deal with the fact that we don't find every mineral in every rock. We have to deal with the fact that not every mineral records all the processes happening at all different temperatures. So new methods actually bring us new potential to use, let's say, different minerals or to look with the same minerals at other temperature ranges. Okay, quick look at zircon, although I think everybody knows already about it. So the mineral zircon is especially suited for geochronological applications, mostly because it incorporates uranium and thorium into its crystal lattice, so as a substitution for the zirconium. And it's extremely stable, both mechanically and chemically. So it doesn't matter if we have sedimentary transport or chemical reactions taking place. Zircon is a pretty stable mineral that can serve as a good archive for the geochronological information. And of course, it occurs widely throughout the geological record. So we have many rocks that we can actually use if we want to date zircon. A short note on the structure that is shown here on the left side. So zircon is a nesosilicate or an orthosilicate, which means that its structure consists of isolated SiO4 tetrahedra, so the yellow things here. And we also have zirconium or 8 polyhedra, which are shown in the slide blue. And we see that the tetrahedra are isolated, but these polyhedra actually form chains, or they are interconnected, and they also interconnect with the SiO4 tetrahedra. So what's the idea behind Zircon Raman dating? The main phenomenon that is studied is radiation damage that's accumulated from the alpha disintegration of uranium and thorium nuclides, and of course their daughters during the decay. And what happens is that basically the radioactive nuclide emits an alpha particle, and the remaining heavy nucleus recoils in the opposite direction. And both of these processes lead to like the breaking of bonds in the lattice. Basically, the heavy nucleus collides with the crystal lattice around it and breaks bonds, distorts bonds, and this leads like to a destruction of the crystalline structure. See this here on the left in the sketch, where we have like a region where several of these recoil processes happened. And we can see that in the middle of the model, basically the crystalline structure is completely obliterated. And around it, we can see that, well, there are still bonds, but they're not in their original orientation anymore. They don't have their original length and so on. So what we basically get from the alpha emission process is a crystal lattice that is partially amorphous and partially distorted and disordered. What does this look like over geological timescales? Well, as we can see here up top, is that if we start with a very crystalline zircon with a very well ordered lattice, and step by step over time the alpha decay happens and we start accumulating small regions where the crystal lattice is not intact or is not the same anymore. And over time, they start overlapping, they start forming networks until, well, we have like only some crystalline islands that are remnant between the amorphous or distorted matter. And in the end, we get like a completely metamict or amorphous zircon. So as we can see here, it's a process that happens over time. And as we know how fast the decay of the uranium and thorium isotopes happens, we know pretty well about the rate at which this process happens. And this has called forth the idea of using this mechanism of radiation damage for dating. So this idea is not new. It's basically the idea of dating damage induced by radiation is over 100 years old, and then later was applied more specifically to zircon. But the Zircon Raman dating as a technique or an idea is basically about 20 years old as technology progressed and the different methods to measure the radiation damage have developed. So the requirements for dating are basically the same as with all other methods. We need to measure the daughters or the effect of the radioactive process. In this case, we need to measure how much damage has been accumulated in the lattice. And we need to measure the parents. So we need to know how much uranium and thorium is there, so that we can calculate back how much has decayed over time and at what rate. So how does this work? For the H equation, we can basically use the alpha dose as a measure of the accumulated damage. So the alpha dose is simply the number of decay processes that have taken place during the lifetime of the zircon. So it depends, first of all, on the concentration of radioactive nuclides, which would be like the 238, 235 and of uranium and 232 of thorium. And of course, it depends on time. The longer the time, the more alpha events will have taken place. And we can basically take this equation here, the big alpha dose equation, simplify it a little bit and rearrange it for the H to get this H equation. And if we look at it closely, in this H equation, we have like some physical constants in there, like the decay constant, we have like the nuclide mass, Avogadro's constant, and only those two variables here, which are the d alpha and EU. EU, I hope that you know it, it's the effective uranium concentration. It's just a normalization of the uranium and the thorium content to the decay rate of uranium-238. And the d alpha is, of course, like a measure of the alpha dose. So this formula basically means what I told you before. If we can measure in a zircon a measure of this alpha dose, a measure of the radiation damage, and the effective uranium, which is the concentration of uranium and thorium, we can calculate the Zircon Raman H from it. So the first thing that we actually need, well, we already know how to measure uranium and thorium in zircon grain. I mean, many people do it routinely. What we need to know is actually how to measure this damage. So we need some calibration of a damage-dependent signal against this alpha dose. This can be done by many different methods. So here's just a list which is not even exhausted. So there are more methods that we can actually use for measuring radiation damage. But what I want to focus on today is the Raman spectroscopy, which is probably one of the easier picks from that list. So how does this basically work? Here's just a sketch of a setup of a Raman spectrometer. So what we have is like a sample chamber down here, usually attached to a microscope so that we can navigate the sample. And once the sample is in there, we can shoot on it with a laser. Usually we have different options for different laser wave numbers, but it doesn't matter so much in that context. and then the laser will be put on the sample. It will lead to the emission of a Raman signal, and that signal is then sent through a spectrometer and onto a detector so that we can basically save it and analyze it. So this is basically how the measurement works, and what we get from this measurement is such a Raman spectrum. So we get a Raman shift, which is basically a wave number or a reciprocal wavelength. So it's like a measure of the frequency of the light signal, and we get the intensity, of course, like how much light at which frequency has come to the detector. And what we see in here are different Raman peaks. So we can give a name to all of them, but I only chose some to not be too confusing here. And every one of these peaks basically corresponds to a vibration within the zircon crystal lattice. So as I said, for the rest of the talk, I will always refer back to these peaks. So just have to remember they're like the new 1, the new 2, the new 3, and the so-called ER peak, which I would say are the most studied in zircon. So that brings me to the question, how does the radiation damage in the zircon actually affect the Raman spectrum? And we can see this on the left. So in gray, we have the spectrum of a synthetic zircon, which means a zircon that has never accumulated any radiation damage. And we have this green spectrum, which is a spectrum of a zircon that is strongly radiation damaged. And what we can see here pretty straightforwardly is that the Raman peaks, due to the accumulation of damage, shift towards the left, and they become substantially broader. So we see all of the peaks that are here have become broader, and they have shifted to the left. We can also see this on the right. So plotting the band position against the band width, the so-called omega gamma plot, we can see for several data points, for several zircon samples, that we get like these arrays of data here. And they all belong to a common trend of damage accumulation that starts somewhere up on the left side, where we have like very narrow bands, a low bandwidth and a high band position, and then they shift during damage uptake towards lower positions and higher bandwidths. So this is basically the effect of the damage on the Raman spectrum. So the next step there logically is to calibrate this against the alpha dose, so that we can basically in our H equation substitute this d alpha by something that we measured on a natural zircon. So what we did for this, we gathered like different rock samples from volcanic zircons with like a big spread in alpha dose. And for each of them, we determined the alpha dose from the H and the uranium and thorium contents, and we measured the Raman bandwidths, or we took Raman spectra of all of these zircons. And then what you can see here is a plot of the Raman bandwidth, like of the 4 Raman bands I showed you. It's called gamma here. And this is plotted against the alpha dose for every individual zircon. And basically for each of these different bandwidths, for each of the different Raman bands, we get a single calibration line that consists of 2 parameters. One is the gamma 0, the intercept, which is basically the bandwidth that we expect a zircon to have that has no radiation damage at all. And the other is the slope, which is the dose response, which is kind of the sensitivity of this Raman band to the radiation damage. And once we have established this calibration line with the dose response and the 0 damage bandwidth, we can actually, for every measurement that we make on any natural zircon, calculate a D, which is like an equivalent to the alpha dose. And by just measuring the bandwidth of a Raman band, subtracting this 0 damage bandwidth and dividing by the dose response. Okay, so I have a few examples here for the dating. One is from a Duluth complex sample FC1. So here we measured for a set of zircons the D from the Raman bandwidth and the effective uranium using SIMS, so secondary ion mass spectrometry. And as we need the ratio between the D and the EU, I just plotted the estimated damage against EU and fitted a regression line to it. It's like isochron dating, and just took the slope of that regression line and substituted it here for this ratio of D alpha over EU. And what I got was an age of 1033 plus minus 33 million years, which is, I would say, a nice result. We also see we get a really nice array of data here in this plot. The only problem, I would say, is that the uranium lead age of this rock is slightly older than this. For a second example, I took Plešovice zircon from Czech Republic and did the Raman measurements. Then I did electron microprobe measurements of uranium and thorium and did the same plot, and then calculated for 3 different Raman bands the age. So what we see in the different colors are just different Raman parameters that are used for calculating the age. And what we get are ages that are roughly at 220 to 260 million years. So let's say about 240. The data look really good. But again, we have the problem, the uranium lead age of Plešovice zircon is nearly 100 million years older. So what's the problem here? Of course, we're dealing with a thermochronometer. So that means that somehow temperature must have an influence on the Raman spectrum and the radiation damage. And in the case of radiation damage, we have a process called annealing, which is basically the self-repair of the zircon lattice at high temperatures. And if this happens, if annealing happens, of course, our age is not the same as the formation age, or we can say the damage that we measure is not actually the alpha dose, but it's some value that is lower than the alpha dose because some of the damage has been lost from the zircon. So what can we do about this? Well, as with all the thermochronometers, we can perform kinetic experiments to get to know this process of annealing better and estimate a closure temperature. This is what we did. So we took a zircon sample and subjected it to heating at different temperatures and different times, and then looked how the zircon Raman spectrum changed with temperature and time. And well, on this slide, I just want to show you again these omega gamma plots, so band position versus band width. You remember before when we looked at it, I showed you the accumulation trend here in gray from upper left to lower right. And now we have these colored symbols, which are basically zircons from an annealing experiment. And there we can see that from the starting material in black, once we start annealing, we go up again. So we switch back basically our Raman spectrum or peaks to higher wave numbers, and we switch to the left. So that means that our Raman bands become narrower again. So until we at some point approach basically a fully crystalline synthetic zircon. There's one outlier here, which is the nu 2 Raman band, which actually does not switch back to higher wave numbers first, but during the initial stage of annealing even goes to lower wave numbers. The second odd observation, which also has been made before, is that actually the annealing process is not the reverse of the accumulation process. So these annealing data do not lie along the accumulation trend, but they're off it, and they follow like a 2-stage pattern. This has usually been interpreted as a 2-stage process that happens during annealing, which means just that during one stage of annealing, a certain type of defects, in this case point defects, is eliminated, and then in a second stage, the amorphous parts in the crystal lattice crystallize again. Okay, To quantitatively study the annealing kinetics, I just focused on 3 of our Raman bands and performed isothermal annealing experiments. So I did like series of experiments at the same temperatures and over a longer time, and then repeated this for different temperatures on zircon separates from the same sample. And this is shown here. So we can see a change in phi, which is relative annealing. Let's say it goes from 0 to 1, 0 meaning no annealing, 1 meaning the sample is completely crystalline. And what we can see is that for all the temperatures, we have an increase in the degree of annealing over time. And what we can also see, higher temperature means higher degree of annealing. When we then compare the different Raman bands, we can see that the nu2 and the nu3 have, like, for the same temperature and time conditions of the experiments, more or less the same degree of annealing, so they behave nearly the same. But the ER band actually shows higher degrees of annealing at basically all times and temperatures. We then took these data and fitted kinetic models to it. Like, one is called an Avrami type model, the other a distributed activation energy model, and determined closure temperatures from it from the Dodson equations. So what we got out were closure temperatures, one for each of the models that we calculated. And here on the left, like the 3 lower estimates are the ones from our study. So we can see, like, for the nu2 and the nu3 Raman band, we get a closure temperature of roughly 350 degrees. And then something interesting happens. As I showed you before, the ER band usually shows like a higher degree of annealing than those 2 bands. And this means, like, the ER band is actually more sensitive to annealing. So the Zircon Raman method does not only have one closure temperature, but depending on the part of the Raman spectrum that we look at, we have different temperature sensitivities. And so this ER band actually has a closure temperature of about 280, 290 degrees. So this was actually a very new finding, and we didn't expect to get out several closure temperatures. We thought we would only get one, but until now it has been repeatedly shown that actually the ER band is more sensitive to temperature than the others. If we compare this to previous estimates of the annealing temperature for the Raman spectrum, we see they're pretty much scattered, but we're somewhere in the middle of the previous estimates. On the right side, just a short note, there we have the partial annealing zones for the different Raman signals, and between like 20% and 80% annealing. And there we can also see that the partial annealing zone, so the zone where only a part of the damage is annealed, is actually pretty broad for all 3 bands. And of course, we see again the green zone here, the one of the ER band, is shifted towards lower temperature, showing that this band is more sensitive to annealing. So this leaves us with the question, what can we now do with this tool? And like, one of the prospects that I'm currently exploring at the University of Calgary is multi-method zircon dating. As we can see here, there are several methods, dating methods, that we can apply to zircons, such as uranium-lead, uranium, thorium, helium, and fission track dating, and now also the Raman dating. And we can see here all of these methods operate on a different in a different temperature window. So if we can basically apply all of these methods to one sample, we can actually get like a pretty solid thermal history just from dating zircon. And adding the Zircon Raman method to the other methods is not a big effort, as Raman is pretty quick and cheap, and it can give additional information on the thermal history. Of course, if we then do Zircon Raman dating on those samples, it also gives us some direct radiation damage information, which could be interesting for the other dating methods as well. Another prospect is the annealing detection, or like the in-depth study of thermal history from Raman alone. And this actually also works by comparison of like the less and the more sensitive signals in the Raman spectrum. So if we calculate a damage estimate from the nu2, the nu3, and the ER band, so different Raman bands, we would usually expect for the same zircon that they're the same, right? That every Raman signal gives us like the same alpha dose or the same damage estimate for such a zircon. So during accumulation, this is actually true. If we look at those damage estimates, they all grow evenly, and such a ratio between them, in this case between the D2 and DER, should be constant. But once the zircon is put to high temperatures upon annealing, as we saw from the experiments, all of these D values, all of the damage that is in the lattice decreases, but the DER will decrease more than the others because it's more sensitive, and this will lead to an increase of this D2 DER ratio. You can also show this on natural data. So here on the right, we see a CL image and a map of a zircon from KTB borehole in Germany. This is a sample from 9,000 meters depth at about 260, 270 degrees Celsius. So one that was really deep down, where we know that has seen some radiation damage annealing. And what I mapped here on the crystal is actually this D2 DER ratio. And we get values of about 1.5 to 3 there, although upon accumulation only, we would only expect a value of 1. And we can compare it here in this plot, for example, with FC1 zircon, which has not been annealed at all during its thermal history. This one actually shows the expected ratio of 1, but this KTB zircon in orange gives a much higher value, which indicates annealing. And as I said, we know the zircon spent lots of time deep down in a borehole, so we can actually confirm this by a Raman measurement. Another really interesting prospect then is also single grain multi-spot dating. So as Raman is a method that, as I said, is pretty quick and that we can also use to map single grain zircons, we can actually also determine multi-spot ages on single grains and see if there are maybe some zonings that are revealed, some age zonings, if we can also maybe detect zones which are not so suitable for Raman dating or not good also for other methods if we want to do, for example, laser ablation uranium lead dating later. And so this is a very helpful feature of Raman spectroscopy that can be incorporated into the dating process. Okay, so to give you a short overview again about what our contributions to the Zircon Raman dating were, I can refer you to the publications that we wrote on it, which basically include the calibration of the damage against the Raman spectrum, the determination of the closure temperature for Zircon Raman dating, and data analysis of Raman spectra for Raman dating, which includes annealing detection and also some Raman-specific artifacts. And yeah, at this point, I'm done with my talk and I'm open for questions. Thank you.